At first blush, this problem looks kind of silly. It's a 55-kilogram hunter standing on frictionless ice, and he shoots a bullet. And then you're asked for the recoil speed of the hunter. I mean, if you're standing on a frictionless pond, I don't know exactly what you're hunting. This seems kind of silly, but really what it's getting at is this. Imagine firing a gun. And when you fire a gun, the bullet goes forward, and the gun gives you a kick backwards. And so really what we're trying to figure out is basically what's the size of the kick. And if we imagine you were standing on frictionless ice and the gun gave you a little bit of a kick, how fast would it push you backwards? So it's going to allow us to estimate the size of the kick. Now I'm going to think about this. I think it's a pretty good thump. And so it would make you move backwards at a noticeable speed, but not at highway speeds. Okay, it's going to be kind of a noticeable speed, but kind of a small speed. That's kind of what I'm anticipating for this problem. And it looks like we're going to want to treat this as a conservation of momentum problem, because at the start you have the hunter and the gun and the bullet standing still, and so the momentum is 0. At the end, you have the hunter moving backwards, the bullet moving forwards. The momentum is still 0. So we're going to solve this as a problem of conservation of momentum. And to do that, we'll remember our basic rule. The initial momentum of an isolated system is equal to the final momentum. And it's frictionless ice. And so everything, and we're going to not worry about other external forces. And so we can treat this as an isolated system. So we're going to draw a before and after picture to visualize this scene. Okay, and our before picture looks like this. We have the hunter, okay, holding a gun, like so, and the momentum is 0. Just the magnitude of the momentum is 0. Our after picture looks like this. Okay, after, the hunter has fired the rifle, okay? So the bullet's moving this way with the speed v sub b. That's the speed of the bullet. The bullet has a certain mass. The hunter has a mass m sub h. And the hunter is moving backwards at a speed v sub h, okay? Now the final momentum is equal to 0. Because we know the initial momentum and the final momentum have to be equal, since it's frictionless ice, this is an isolated system. And so I can just equate these two momentums. The momentum of the bullet is equal to the momentum of the hunter. And so I can just write this. The mass of the hunter times the speed of the hunter is equal to the mass of the bullet times the speed of the bullet. That's the basic relationship that we can use to solve this problem. And with that, we're ready for a solution. So let's rewrite this relationship. It's mh times vh is equal to mb times vb. Now we're trying to solve for the speed of the hunter, vh. So vh is equal to vb times mb over mh. That's what we're looking for here. Now it turns out we know all of these numbers. Okay, the mass of the bullet, it's a 42-gram bullet. That's 0.042 kilograms. The mass, oh, and I can see I made a little typo here. This is supposed to be m sub h. That's the mass of the hunter. Okay, the mass of the hunter is 55 kilograms. Okay? The speed of the bullet is 620 meters per second. And so we have all the numbers that we need to be able to calculate the speed of the hunter. And if we do that, we get a speed of 0.47 meters per second. That's our final result. Now let's assess it. And at the start of the problem, I said, think about this. We're going to imagine the kick that the rifle is going to give to the hunter. And imagine that he could actually slide backwards. How fast would he be moving? And it gives him a pretty decent kick, enough to move backwards at 0.47 meters per second. That's approximately 1 mile per hour. And that seems reasonable. We said you wanted to move backwards at a noticeable speed, but not like highway speeds. And that is what we ended up with. And so our assessment is that our result matches our understanding of the way the world works.